In this lesson, we're first going to learn how to factor perfect square trinomials. Then we're going to factor binomials using the difference of two squares formula, the sum of two cubes formula, and the difference of two cubes formula. In my chapter 4.5 video, we learned how to factor trinomials. Remember, a trinomial always has three terms. So this is a trinomial because it has 1, 2, 3 terms. This is a trinomial because it has 1, 2, 3 terms. And this is a trinomial since it has 3 terms. We're going to factor these trinomials pretty quickly. So for an introduction and in-depth lesson of how to factor trinomials, please watch my chapter 4.5 video. We've learned that the first step in any factoring problem is to always check for a greatest common factor. This particular problem has no greatest common factor. So we can now move on to step 2. When you're factoring a trinomial, we set up step 2 this way. We're going to look for two numbers that multiply to give us the product of a times c, where a is the coefficient of the squared term and c is the constant. So a times c would be 1 times 64, which gives us 64, and we need those same two numbers to add to give us the coefficient of this x term, which is 16 in this case. The two numbers that work are 8 and 8, because 8 times 8 gives us 64, and 8 plus 8 gives us 16. Now, in my chapter 4.5 video, we learned that when you have a trinomial where the coefficient of the x squared is a 1, which is the case here, those trinomials are easier to factor. Because once you have these two green numbers, in step 3, you can just insert those green numbers in the parentheses and you'll be done. So let's start by setting up our parentheses. Since our variable is an x, we'll put an x in the first position in each parenthesis, and then we'll insert these green numbers in the blanks. Since this is a positive 8, we'll write a plus 8, and we have another positive 8, so we'll write another plus 8. Notice we have a special case here. We end up with two identical factors, x plus 8 times x plus 8. When that's the case, we can write our answer in condensed form. X plus 8 times x plus 8 is equivalent to x plus 8 squared. So we call this type of trinomial a perfect square trinomial because it factors perfectly as some quantity squared. Let's take a look at the next example. Now, before we try to factor this trinomial, notice that the terms are all out of order. When we factor a trinomial, we need that trinomial to be in standard form. And to be in standard form, we need to put our squared term first. So I'm going to first write 2x squared. Then we want our x term in the middle, so I'll write negative 36x in the middle. And then we put our constant last. So let's put the positive 162 last. Now we've written our trinomial in standard form. Now we can proceed to factor. The first step of any factoring problem is to check for a greatest common factor. The greatest common factor here would be 2. So since there is a GCF, we need to factor out that GCF. So we'll put the 2 outside of parentheses. And then let's see. 2 times x squared will give us 2x squared. If you take negative 36 divided by 2, you'll get negative 18. So 2 times negative 18x will give us negative 36x. And then if you take 162 divided by 2, you'll get 81. So 2 times a positive 81 will give us our positive 162. Now we've factored out the GCF. Now we need to make sure to include the GCF in our final answer, but let's just ignore the GCF for the time being so that we can focus on factoring this trinomial right here. For step 2, we need to find two numbers that multiply to give us the product of the squared term times the constant. Now be very careful. Do not look at the original problem. Once you've factored out your GCF, you want to look at this trinomial for the rest of the problem. So we need our two numbers to multiply to give us 1 times 81, which gives us 81, and we need those same two numbers to add to give us negative 18. The two numbers that work are negative 9 and negative 9, because negative 9 times negative 9 gives us 81, and negative 9 plus negative 9 gives us a negative 18. Now, once we factored out the GCF, we were left with a trinomial where the coefficient of the squared term is a 1. When the coefficient of your squared term is a 1, step 3 is very quick. For step 3, we just draw our parentheses, and we'll insert an x in the first position in each parenthesis, and then we'll insert these green numbers in the blanks. So we'll put a -9 in one parenthesis and a -9 in the other parenthesis. Then our GCF was 2, so we'll make sure to put the 2 out front. Now notice we have another special situation here. We have two identical factors, x minus 9 and x minus 9. So we can rewrite this in condensed form as 2 times x minus 9 squared. We would again call this trinomial a perfect square trinomial because when we factor, it factors perfectly as some quantity squared. Let's look at one last example of a perfect square trinomial. Whenever we're factoring, the first step is always to check for a greatest common factor, but there is no greatest common factor for this perfect square trinomial. Step 2, we need to find two numbers that multiply to give us a times c. So that would be 4 times 25, which gives us 100. And we need those same two numbers to add to give us the coefficient of the x term, which is 20. The two numbers that work are 10 and 10 because 10 times 10 gives us 100 and 10 plus 10 gives us 20. Now, if the coefficient of your squared term is a 1, that was the case for this problem, and here after we factored out the GCF, the coefficient of our squared term was a 1. When the coefficient of your squared term is a 1, once you have these two green numbers, step 3 is very quick. You just insert these two green numbers in the blank like we did here, or like we did here, and you've got your final answer. Now, when the coefficient of your squared term is not 1, step 3 is a little bit harder. In my chapter 4.5 video, we learned that when the coefficient of your squared term is not 1, for step 3, we learned 3 different methods. You can use whichever of those 3 methods you prefer. I'm going to use my favorite method here, which I call the factor and divide method. For that method, we set up our parentheses. Now, when the coefficient of the squared term was a 1, we put a 1x and a 1x in each parenthesis. Here, since the coefficient of the squared term is a 4, we're going to put a 4x and a 4x in each parenthesis. If this was a 10x squared, then we would put a 10x and a 10x. Then we insert these green numbers in these blanks. So we'll put a plus 10 and a plus 10. But now this answer is not correct. We should be able to FOIL this out and get back to our original problem. But I notice right away that 4x times 4x gives us 16x squared, but we're supposed to only have 4x squared. Well, that's why this method is called the factor and divide method. We factored, but we still have to divide. We examine each parenthesis separately, and we divide each parenthesis by its GCF. So if we look at the first parenthesis here, what is the GCF between 4x and 10? The GCF would be 2. So we're going to divide this parenthesis by 2. Then we look at the next parenthesis separately, and we ask ourselves, what is the GCF between 4x and 10? Again, it would be 2. So we divide this parenthesis by 2. And let's see what that leaves us with. 4x divided by 2 gives us 2x, and 10 divided by 2 gives us a positive 5. Again, over here, 4x divided by 2 gives us 2x, and 10 divided by 2 gives us a positive 5. Now we've factored this trinomial, but notice that we end up with two identical factors. We can write our final answer in condensed form as 2x plus 5 squared. Now, on this first page here, we factored trinomials. For the remainder of this lesson, we will no longer factor trinomials. We are going to move on to factoring binomials. So put all of these methods for factoring trinomials aside, because when we factor binomials, we need to learn completely different methods. A trinomial involves 3 terms. A binomial involves 2 terms. So this is a binomial because it has 2 terms. All of these, in fact, are binomials because they all involve 2 terms. First, we're going to learn how to factor a special type of binomial that can be factored using the difference of two squares formula. But first, we have to review what a perfect square is. Any perfect square can always be written as some quantity squared. So for example, 1 is a perfect square because we can write 1 as 1 squared. 4 is also a perfect square because we can write 4 as 2 squared. 9 is also a perfect square because we can write 9 as 3 squared. And here's some more examples of perfect squares. This is a list of all of the perfect squares up to 100. We could, of course, keep listing perfect squares forever. Now, we can have numbers that are perfect squares, like 16 or 25 or 36, but we can also have variables that are perfect squares. For example, x squared is a perfect square. In fact, it's already written as some quantity squared. X to the fourth is also a perfect square. Remember, this is a perfect square as long as it can be rewritten as some quantity squared. And we could rewrite x to the fourth as x squared squared. Because remember, when you raise an exponent to an exponent, you multiply those exponents, and 2 times 2 gives us 4. There are infinitely many more examples of perfect squares involving variables, but we'll look at just a couple more examples. 9x squared is a perfect square because it can be rewritten as some quantity squared. Let's see, to get 9, we'd have to square 3, and to get x squared, we'd have to square x. One last example, 64x to the fourth is a perfect square. We know it's a perfect square because we can rewrite it as some quantity squared. Let's see, 8 squared will give us 64, and to get x to the fourth, we'd have to square x squared. So 64x to the fourth is a perfect square because it can be rewritten as 8x squared squared. Now that we've reviewed some examples of perfect squares, let's learn how to factor these binomials. If you have a binomial where both terms are perfect squares, for example here, x squared is a perfect square, we said that up here, and 16 is a perfect square, we said that up here. And if you have a subtraction sign in the middle, you must have a subtraction sign in the middle, then to factor this binomial, we use the difference of two squares formula. The difference of two squares formula says that when you have two perfect squares, we'll call one of those perfect squares a squared and the other perfect square b squared. And then if you have a subtraction sign in the middle, this can be factored as a minus b times a plus b. So let's practice using this formula. So the first step in any factoring problem is always to check for a greatest common factor. There is no greatest common factor here. Now, if you notice that you have a binomial, so you have two terms, and if both terms are perfect squares, and if you have a subtraction sign in the middle, then we can factor using this formula. We just have to figure out what is our A and what is our B so that we can plug those values into the formula. I recommend that you start by rewriting this first quantity as some quantity squared. Well, x squared can simply be written as x squared. Next, we want to write this quantity as some quantity squared. 16 can be rewritten as 4 squared. And then since we have a subtraction sign in the middle, we'll add our subtraction sign here. Now, what's inside these parentheses in purple is our A and our B. A is the quantity inside these first parentheses here, the quantity in purple. So A is x. And B is the quantity inside these second parentheses. So B is 4. Now that we've identified our A and our B, we just have to plug those values into this formula. So I'm going to start by copying this formula down here. So we'll start by drawing our parentheses, and then we'll put a minus sign in one parenthesis and a plus sign in the other. If we flipped the plus and the minus sign around, that would be completely fine. Now A is x, so wherever we see A in the formula, we'll write x. I see an A here, and I see an A here. And B is 4, so wherever we see B, we're going to write 4. So we'll write 4 here, and here we'll write 4 as well. and there was no GCF, so we don't need to put any GCF out front. So we fully factored this binomial using the difference of two squares formula. A great way to check your work would be to FOIL this out, and you'll see when you FOIL this expression, you get x squared minus 16. Let's try another problem. Now, the first step in any factoring problem is always to check for a greatest common factor. Again, there is no greatest common factor for this problem. Now, we notice that we have a binomial. If both of these terms are perfect squares, then we can use the difference of two squares formula to factor. So let's see, can we rewrite this first term as some quantities squared? Well, 2 squared gives us 4, and p squared gives us p squared. So it looks like this is a perfect square. And can we rewrite 1 as some quantity squared? Yes, 1 is just 1 squared. So both of these are perfect squares, so we can use our difference of two squares formula. We just have to identify our a and our b so that we can plug it into the formula. A is the quantity inside these parentheses here, the quantity in purple, which is 2p. And b is the quantity inside these second parentheses, in purple again, so b is 1. Now I'm going to copy down this difference of two squares formula here for our reference. And now we just have to plug our a and our b into the formula, and we'll be finished. So we'll start by drawing our parentheses, and we can put a minus sign in one of the parentheses and a plus sign in the other. Let's see, a is 2p, so we'll plug in 2p here, and b is 1, so we'll write a 1 here. Again, a is 2p, and b is 1. So we fully factored this binomial using the difference of two squares formula. Let's take a look at problem number 6. The first step in any factoring problem is, of course, to check for a GCF, but again, there is no GCF here. Now, can we use the difference of two squares formula to factor this binomial? No, we cannot, because the difference of two squares formula only applies when you have two perfect squares with a minus sign in the middle. Here we have two perfect squares. X squared is a perfect square, and so is 25, but we have a plus sign in the middle. If you have two perfect squares with a plus sign in the middle, you of course check for a GCF. But if there's no GCF, you need to stop because it's impossible to factor. We call this the sum of two squares. Since it's two squares with an addition sign in the middle, you cannot factor the sum of two squares. It's impossible. So when you encounter the sum of two squares, make sure to check for a GCF. And if there is no GCF, we say that it is prime. It cannot be factored. Let's take a look at the last two examples. You might notice here, we have a plus sign in the middle. But we first have to check for a GCF. This plus sign might change once we factored out the GCF. Notice the first term is negative. If your first term is negative, our GCF must be negative. So I'm going to put a negative right here so I don't forget. Then we need to ask ourselves, what's the largest quantity that multiplies into both of these terms? That would be 3. 3 multiplies into 75, and 3 multiplies into 27. So our GCF will be negative 3. So since there is a GCF, we need to factor that GCF out. So we'll put the negative 3 outside of parentheses. And then we need to ask ourselves, if we were to distribute negative 3 times what will give us negative 75x to the 4th? Well, if you take negative 75 divided by negative 3, you get 25. So negative 3 times 25 will give us negative 75, and we also need x to the 4th, so we'll add x to the 4th. Then we need to ask ourselves, if we were to distribute negative 3 times what will give us 27y squared? Well, 27 divided by negative 3 gives us a negative 9. So negative 3 times negative 9 will give us positive 27, and then we need to add a y squared. Now that we've factored out our GCF, now notice we have a minus sign in the middle. So if these are both perfect squares, since we have a minus sign in the middle, we can use the difference of two squares formula. And we're of course going to need to include the GCF in our final answer, but for now we're going to ignore it as we focus on factoring this binomial here. So to find our a, we need to rewrite 25x to the 4th as some quantity squared. 5 squared will give us 25, and x squared will give us x to the 4th, because remember, when you raise an exponent to an exponent, you multiply those exponents. So 2 times 2 gives us 4. Then, to find our b, we need to rewrite 9y squared as some quantity squared. 9 can be rewritten as 3 squared, and to get y squared, we'd have to square y. So these light purple quantities inside of the parentheses represent our a and our b. A is 5x squared, and b is 3y. Be careful when you're defining your a and your b. Don't include these outer squares. Only include these light purple quantities that are inside the parentheses. Now that we've identified our a and our b, we just need to use this formula to write our final answer. So I'm going to copy this formula down here for our reference. Okay, so now let's fill in a and b. A is 5x squared, so we'll write 5x squared here, and b is 3y, so we'll write 3y here. Again, a is 5x squared, and b is 3y. Now be very careful. Don't forget to include the GCF in your final answer. And this is our final answer. We've factored this binomial completely. Let's look at one last example where we're using the difference of two squares formula to factor a binomial. So in order to use the difference of two squares formula, you need a minus sign in the middle, and you need both of these terms to be perfect squares. You'll notice 2 is not a perfect square, and neither is 512. In fact, x to the fifth or x aren't perfect squares either. But remember, you always first have to check for a GCF before you try to use the formula. And there is a greatest common factor for this problem. 2 multiplies into both 2 and 512, and x multiplies into both terms as well. So our GCF is 2x. So since there is a greatest common factor, let's factor out that GCF. We'll put the 2x outside of parentheses. 2x times x to the fourth will give us 2x to the fifth. Remember, when you multiply x times x to the fourth, you add the exponents. So 1 plus 4 gives us the 5. Then we need to ask ourselves, what do we need to multiply 2x by to get negative 512x? Well, if you take negative 512 divided by 2, you'll get negative 256. So 2x times negative 256 will give us negative 512x. Now that we've factored out the GCF, we'll make sure to include it in our final answer, but we can ignore it for the time being as we focus on factoring this binomial. Now this binomial is set up perfectly. We have two perfect squares with a minus sign in the middle, so we can use this difference of two squares formula. We just have to figure out what our a and what our b is. To figure out what a is, we need to rewrite this first quantity here as some quantity squared. X to the fourth can be rewritten as x squared squared. And then to figure out b, we need to rewrite 256 as some quantity squared. To help you figure that out, in your calculator, you could take the square root of 256. And the square root of 256 is 16. That means that 256 can be rewritten as 16 squared. Now, what's inside the parentheses in light purple, not including these outer squares, is our a and our b. So a is x squared and b is 16. Now that we've determined our a and our b, let's use this formula to write our final answer. So I'm going to copy this formula down here, and we'll start by drawing our parentheses, putting a minus sign in one parenthesis and a plus sign in the other. A is x squared, so we'll write an x squared here, and b is 16, so we'll write a 16 here. Again, a is x squared, and b is 16. Then we need to make sure to include our GCF in our final answer. Now be very careful, because it might seem like we're finished, but we're not. Sometimes when you're factoring binomials, you end up with an answer that can be factored further. Notice here we have x squared minus 16. We have two perfect squares with a minus sign in the middle. In fact, this is the exact problem we factored in problem number 4 here. We factored x squared minus 16 using the difference of two squares formula to get this. So we can use the difference of two squares formula to factor x squared minus 16. And I won't go through all of the work again since we did it right here. When you factor x squared minus 16 using the difference of two squares formula, you get x minus 4 times x plus 4. Now what about x squared plus 16? Can this be factored further? No. While we have two perfect squares, we have a plus sign in the middle. So this is similar to problem 6. We call this the sum of two squares, and the sum of two squares cannot be factored. So we're just going to bring down x squared plus 16. It cannot be factored any further. And then, of course, we need to bring down our greatest common factor. So this is our final fully factored answer. So when you're factoring using the difference of two squares formula, be careful. When you get to your final answer, double check it and ask yourself, do either of the factors contain two perfect squares with a minus sign in the middle? Here, no. X is not a perfect square, so we don't have two perfect squares with a minus sign in the middle. Here, we didn't either. 2p is not a perfect square, so we don't have two perfect squares with a minus sign in the middle. But here, we ended up with two perfect squares with a minus sign in the middle, so we needed to factor this further using that difference of two squares formula. On this next page, we're going to continue to factor problems involving two terms, but these binomials will not involve perfect squares. Instead, they will involve perfect cubes. We're going to learn two formulas, the formula for the sum of two cubes and the formula for the difference of two cubes. Before we discuss those formulas, let's review some examples of perfect cubes. A perfect cube can always be written as some quantity cubed. So for example, 1 is a perfect cube because we can write 1 as 1 cubed. 8 is a perfect cube because we can write 8 as 2 cubed. 27 is a perfect cube since we can write 27 as 3 cubed. And I've continued listing several other examples of perfect cubes. Now we could list infinitely many more perfect cubes, but here's all of the numbers that are perfect cubes up to 1000. Now, as we saw with perfect squares, you can have numbers that are perfect cubes, and you can also have variables that are perfect cubes. For example, x cubed is a perfect cube. Remember, anything is a perfect cube if it can be written as some quantity cubed. And x cubed is already perfectly written as a quantity, x in this case, cubed. X to the sixth is another example of a perfect cube. X to the sixth is a perfect cube because we can write it as some quantity cubed. Let's see, what do we have to cube to get x to the sixth? Well, x squared cubed will give us x to the sixth. Because remember the properties of exponents? When you raise an exponent to an exponent, you multiply. So 2 times 3 gives us 6. Here's another example of a perfect cube. 8x cubed is a perfect cube because we can write it as some quantity cubed. Let's see, to get 8, we'd have to cube 2, and to get x cubed, we'd have to cube x. So 8x cubed can be rewritten as the quantity 2x cubed. And let's look at one last example. 343x to the sixth is a perfect cube because we can write it as some quantity cubed. Let's see. To get 343, we'd have to cube 7. And to get x to the sixth, we'd have to cube x squared. Now let's look at the previous page for a minute. On the previous page, we learned how to use the difference of two squares formula. We said if you have two perfect squares, for example, x squared is a perfect square and 16 is a perfect square, and if you have a minus sign in the middle, we use our difference of two squares formula. Now this is called the difference of two squares formula because you have to have a subtraction sign in between your two squares. Here we saw two perfect squares with a plus sign in the middle. We call this the sum of two squares, and the sum of two squares cannot be factored. Now cubes are different. If you have two perfect cubes with a plus sign in the middle, you can factor that. So two perfect cubes with a plus sign in the middle can be factored using the sum of two cubes formula. The sum of two cubes formula says if you have two perfect cubes, we'll call those cubes a cubed and b cubed. And if you have a plus sign in the middle, we can factor it using the sum of two cubes formula. It's called the sum of two cubes since we have a plus sign in the middle of two cubes. And the sum of two cubes formula looks like this. This formula might look a little bit complicated at first, but all you have to do is determine your a and your b and plug it into this formula, and you've got your answer. So let's take a look at two examples here. The first step in any factoring problem, before you decide what type of formula you're going to use, is you need to check for a greatest common factor. For this problem here, there is no greatest common factor. We notice that we have a binomial here, since we have two terms. If you have a binomial, you have to decide, are these two terms perfect squares or are they perfect cubes? Because that will tell us how to factor. X cubed is a perfect cube. It's not a perfect square, and 64 is also a perfect cube. We see it on our list here. So it looks like we're dealing with two perfect cubes with a plus sign in the middle. So if you have two perfect cubes with a plus sign in the middle, we use this formula here. We just have to determine our A and our B. To find our A and our B, let's start by rewriting x cubed as some quantity cubed. We can rewrite x cubed as the quantity x cubed. Next, we want to rewrite 64 as some quantity cubed. You can either look at our list up here and see that 64 is 4 cubed, or you could find the cubed root button on your calculator. And if you take the cubed root of 64, you'll get 4. So that tells us that 4 cubed gives us 64. Now, what's inside these parentheses in light purple here is our A and our B. A is what's in this first parenthesis here, so A is x. And B is what's inside this second parenthesis here in light purple, so B is 4. Notice when you're defining your A and your B, you don't include these outer cubes here. You only write what's inside the parentheses here in light purple. Now that we've defined our A and our B, we just need to plug A and B into this formula here. So I'm going to carefully copy this formula down here for our reference. Now, wherever we see A in this formula, we'll plug in x, and wherever we see B, we'll plug in 4. To start, I see A here, so we'll plug in x, and then we'll write our plus, and then for B here, we'll plug in 4. Then we're supposed to take A and square it, so we want to take x and square it, and then we need to subtract A times B, so we're going to subtract x times 4, which I'm going to write as 4x, and then we need to add B squared. B is 4, so we're going to square 4. Now that we've plugged in our A and our B, now we just want to simplify. And it looks like the only thing that can be simplified here is 4 squared. So I've just copied down this exact problem here, but I've squared the 4 to get 16. And this is our final fully factored answer. For your final answer, the addition and subtraction signs that appear in this formula should appear exactly the same way in your final answer. So we see a plus sign here, we should see a plus sign here. Then we see a minus sign, you should see a minus sign in your final answer here. And lastly, we see a plus sign, and you should see a plus sign right there in your final answer as well. Also notice when you're using the formula for the sum of two cubes, you'll end up with a trinomial. In chapter 4.5, we learned how to factor trinomials. So you might be tempted to check to see if this trinomial can be factored. The good news is that whenever you're using the formula for the sum of two cubes, you'll end up with a trinomial that will never be factorable. So when you're using the sum of two cubes formula, you don't ever have to worry about factoring this trinomial any further. This trinomial will always be prime. Let's take a look at another example. Now we notice we have a binomial here, but before you decide if you're going to use the difference of two squares formula or the sum of two cubes formula, first factor out the GCF. Don't make any decisions about what formula you'll use until you've first factored out the GCF. When we're determining the GCF, I notice that our first term is negative. So that means that our GCF will be negative. So I'm going to start by writing the negative so we don't forget. Then the largest number that multiplies into both 81 and 375 is 3. So our greatest common factor will be negative 3. So since there is a greatest common factor, we need to now factor out the GCF. To do that, we put the greatest common factor outside of parentheses, and then we'll ask ourselves, what do we need to multiply negative 3 by to get negative 81x cubed? Well, if you take negative 81 divided by negative 3, you get 27. So negative 3 times 27x cubed will give us negative 81x cubed. Then negative 375 divided by negative 3 gives us a positive 125. So negative 3 times 125 will give us negative 375. Now that we've factored out the GCF, we of course need to include the GCF in our final answer, but for the time being, we can ignore the GCF as we focus all of our attention on this binomial right here. Now, we need to ask ourselves, Are these perfect squares or are they perfect cubes? Because that will tell us how to factor. Right away I see the x cubed, so it seems like we're probably dealing with perfect cubes. I also noticed that 27 is on our list of perfect cubes and 125 is on our list of perfect cubes. So it seems like we're definitely dealing with perfect cubes. And since our perfect cubes have a plus sign in the middle, we want to use this formula for the sum of two cubes. We just need to determine our a and our b so that we can plug them into this formula. To find a, let's start by rewriting 27x cubed as some quantity cubed. 27 can be rewritten as 3 cubed, and to get x cubed, we'd have to cube x. Next, to find b, we have to rewrite 125 as some quantity cubed. To figure that out, you could do two things. You could either look at our list here and see that 125 is 5 cubed, or you could find the cubed root button on your calculator and take the cubed root of 125 and you'll get 5. So 125 can be rewritten as 5 cubed. Now, what's inside these parentheses in light purple here is our a and our b. A is equal to 3x and b is equal to 5. So now I'm going to copy down this formula for our reference right here. And now let's plug our a and our b into the formula. Let's plug in 3x for a and 5 for b. Now I'm going to make a small mistake next. This is one of the most common mistakes that are made. So see if you can catch the mistake. Next, we need to take a and square it. So a is 3x, so I'm going to write 3x and square it. Then we need to subtract a times b, so we'll subtract 3x times 5. And then we need to add b squared. b is 5, so we'll square 5. Now, can you catch my mistake? The mistake was right here. We're supposed to take all of a and square it. A is 3x. As I've written this, the square does not apply to the whole 3x. As this is written, the square only is being applied to the x. So to make sure that we're squaring all of a, to make sure that we're applying this square to the whole 3x, we need to make sure to add parentheses. This is one of the most common mistakes. Now, before I forget, let's also make sure to include our GCF. So I'm going to add the GCF out front. And now we just need to simplify this expression here. We'll bring down the negative 3, and we can bring down this 3x plus 5. Then we're going to square the 3 to get 9 and square the x to get x squared. Here, if you take negative 3x times 5, that will give us negative 15x. And then we're adding 5 squared, so we are adding 25. And here is our final answer. Remember, whenever you're using the formula for the sum of two cubes, you always end up with this trinomial here, and this trinomial will never be factorable. So you don't have to worry about trying to factor this trinomial any further. Also, remember that these plus and minus signs should appear exactly as they do in this formula. So notice you have a plus sign first. We have a plus sign first in both of these equations. Then we have a minus sign. We should have a minus sign here in both equations. And we end with a plus sign. We should end with a plus sign. Now let's look back for just a minute. We learned that if you have two perfect squares with a minus sign in the middle, we factor that using the difference of two squares formula. Then we learned if you have two perfect squares with a plus sign in the middle, you cannot factor it. We call this the sum of two squares, and that is prime. Next, we learned if you have two perfect cubes with a plus sign in the middle, just like we saw here, we have two perfect cubes with a plus sign in the middle. In that case, we factor this using the sum of two cubes formula. The last case is what if you have two perfect cubes, but you have a minus sign in the middle? In that case, we're going to use a formula called the difference of two cubes. So on this page, we're going to learn how to factor the difference of two cubes. Let's start by writing the formula. If you have two perfect cubes, in general, we'll call those cubes a cubed and b cubed. And if you have a minus sign in the middle, the formula that we use to factor is this formula here. Now be very careful. The formula for the difference of two cubes is very similar to the formula for the sum of two cubes. The only difference is that some of the signs are changed. So let's take a look at problem 11 and 12. Now, before you decide what formula to use, before you decide if you should use the difference of two squares formula or the sum of two cubes formula or the difference of two cubes formula, first check for a GCF because that may change things. For this case here, there is no greatest common factor. There is no number other than 1 that multiplies evenly into both 8 and 729. So now we need to ask ourselves, what formula do we use here? Since we see an x cubed and a y cubed, it definitely seems like we're dealing with perfect cubes. 8 and 729 are also perfect cubes. So it looks like we have two perfect cubes with a minus sign in the middle. So if that's the case, if you have two perfect cubes with a minus sign in the middle, you want to use this formula for the difference of two cubes. We just need to figure out what A is and what B is so that we can plug A and B into this formula. To find A, we need to rewrite this first term as some quantity cubed. 8 can be rewritten as 2 cubed. And to get x cubed, we have to cube x. Next, to find b, we have to rewrite 729y cubed as some quantity cubed. So 729 can be rewritten as 9 cubed. You could figure that out either by looking at the chart on the previous page or by taking the cubed root of 729. And the cubed root of 729 is 9. And then to get y cubed, we'd have to cube y. What's inside our first parenthesis is a, so a is 2x. And what's inside our second parenthesis in light purple is our b, so b is 9y. Now, a common confusion here is that people will see this negative here, and they'll wonder if b is supposed to be negative 9y. Or they'll wonder when they're writing this expression here, are you supposed to rewrite negative 729y cubed as some quantity cubed? Or are you supposed to write positive 729y cubed as some quantity cubed? The answer is that when you're rewriting these quantities as some quantity cubed, you always want to consider these quantities as positive values. So that's why I put this negative in the middle to kind of separate it. After we put this negative in the middle, we can just focus on positive 729y cubed and rewrite this positive number as some quantity cubed. Another hint is that when you're using any of the formulas that we've discussed in this lesson, your A and your B should always be positive numbers. So when you're defining your A and your B for any of the formulas we've learned in this lesson, A should always be positive and B should always be positive. Now I'm going to copy this formula down here so that we can fill in our A and our B's. So let's start by filling in 2x for A and 9y for B. Then we need to take A and square it, so we're going to take 2x. And we're supposed to square all of A. So A is 2x. To ensure that our square applies to the whole 2x, we need to put the 2x in parentheses, and then we can add our square. Then we need to add A plus B. So we'll take A, which is 2x, times B, which is 9y. And then we need to add B squared. So we're going to take 9y and square it. Now be careful again here. Our square needs to apply to the whole B. B is 9y, so to make sure that we're squaring the whole 9y, we need to add parentheses around it. Now the square applies to both the 9 and the y. Now we're almost finished. The last step is just to simplify. Let's start by bringing down the 2x minus 9y. Then let's square the 2 to get 4, and we'll square the x to get x squared. Then we can multiply the 2 times the 9 to get a positive 18xy. And then we're going to square the 9 to get 81, and we'll square the y to get y squared. And there's no GCF to put out front, and so this is our final answer. And again, with the difference of two cubes formula, you'll always end up with a trinomial. We see that this is a trinomial because it has 1, 2, 3 terms. The trinomial that you end up with will never be factorable, so you don't have to worry about trying to further factor this trinomial. Also, the way these addition and subtraction signs appear in this formula is exactly how they should appear in your final answer. So we should start with a minus sign, then we should have a plus sign, and then we should have a plus sign. Let's try one last example. Now, if you notice here, 2 is not a perfect square, and it's also not a perfect cube. 432 is not a perfect square, and it's also not a perfect cube. So it seems like we can't apply any of the formulas to this. But that's because we have not yet factored out the GCF. First, we have to factor out the GCF, then we'll see that we can use one of the formulas. The greatest common factor for this problem would be 2, so we need to factor out the GCF. To do that, we put the 2 outside of parentheses. Then 2 times x to the 6th will give us 2x to the 6th. And if you take negative 432 divided by 2, you get negative 216. So 2 times negative 216y cubed will give us negative 432y cubed. Now, we of course will need to include the GCF in our final answer, but we can ignore it for the time being as we focus on factoring this binomial. Now we have to ask ourselves, what formula do we use here? Are we dealing with perfect squares or are we dealing with perfect cubes? While this y cubed is a big hint that we're probably dealing with perfect cubes, 216 is also a perfect cube. If we look back on the previous page, we see 216 listed under our table of perfect cubes. And x to the 6th is also a perfect cube. Again, if we look back, we see x to the 6th listed under our table of perfect cubes. So since both of these are perfect cubes, next we have to ask ourselves, do we have a plus or minus sign in the middle? If we have a plus sign, then we use the formula for the sum of two cubes. If we have a minus sign, we use the formula for the difference of two cubes. Since we see a minus sign here, we're going to use the formula for the difference of two cubes. We just have to find our a and our b and plug it into this formula. To find a, we need to rewrite x to the 6th as some quantity cubed. To do that, you can either just look at the chart on the previous page, or we can think through this logically. Let's see. When we raise an exponent to an exponent, we multiply. So what times 3 gives us 6? 2 times 3 gives us 6. So x to the 6th can be rewritten as x squared cubed. To find b, we need to rewrite this second quantity as some quantity cubed. And again, we're going to put this negative in the middle and ignore it for now. So we're going to focus on just rewriting 216y cubed as some quantity cubed. If you take the cubed root of 216, you get 6. So 216 can be rewritten as 6 cubed. And to get y cubed, you'd have to cube y. Now we can see that a is equal to this light purple quantity inside the parentheses, x squared, and b is equal to this light purple quantity inside the parentheses, 6y. Now I'm going to copy down this formula for our reference right here. Now we want to just plug in our a and our b's. We start with a minus b, so a is x squared, and b is 6y. Then we need to take a and square it, so we need to take x squared and square it, so I'm going to put the x squared in parentheses. Then we need to add a times b, so we'll take x squared times 6y. And then we need to add b squared, so we'll add b, which is 6y. And to make sure that we're squaring the whole 6y, we'll make sure to put the 6y in parentheses and square it. Now, be very careful after all this hard work to not forget the GCF. So I'm going to make sure to put the GCF out front. And now we just need to simplify this. So I'm going to start by copying this first part down because it's already fully simplified. Then to simplify x squared squared, when you raise an exponent to an exponent, you multiply. So 2 times 2 gives us 4, leaving us with x to the 4th. Then, to simplify this, we usually put any coefficients out front. So I'm going to put the 6 out front, and then we list the variables in alphabetical order. So I'll put the x squared first, and then the y. Then to simplify this, we'll square the 6 to get 36, and we'll square the y to get y squared. And we now have our final fully simplified answer.